I return exams at the end of the class so that if you are shell-shocked, you will be shell-shocked in the next class, not in mine. But I thought it would be too cruel for you to be shell-shocked during the Thanksgiving weekend. So I thought, I will sacrifice my class so that you'll have a happy Thanksgiving. So you got all your, hopefully you already saw the mail with your score. Like I said, I am going to record the answers I expected on all those questions. So if you listen to it and change your answers and then bring it back to me, I'll give you additional partial credit because it'll be good for me if you know the answers, by the end of this course. So if you listen to you can always question my answers, but at least that way you will know. Obviously I can't write for every one of the answers why it is wrong. So I will, in discussing this on the recording, I will give some of the popular wrong answers and explain why they are wrong. Okay. Again, as I said, it was mostly, I believe, again, there was about, I think, 54 or something was the highest, which, out of 61. And there were several people in 50s and 40s, which sort of means that the transmission is there. The signal might be weak, but the transmission is there. But it'd be good if everybody gets the answers. And I think I mostly just asked what I already said in the class. Obviously, I wasn't actually even going one level deeper. I was just mostly asking what I said in the class. But that still doesn't mean that, whatever I said is actually captured. That's what I found out. Okay. If you are worried about the scores and so on, please feel free to send me mail. You can continue to have a good Thanksgiving break and then come back to it. That's fine. It's not the end of the world yet. End of the world is in December. So that would be, we can talk about any concerns you might have. Okay. And I also, in the meantime, we'll also try to combine. I'll also try to, in the meantime, I'll also try to put together the remaining parts of your, you also have done, in the grade book, we have things about your other assignments that have already been graded, as well as all the discussions that you took part. That's mostly completion credit, but if you did take part in the discussion, if you posted comments, for any required discussions. I think there were 3 of those. We put all of those also into the grade book. And I think there's one assignment that the TA still has that is trying to complete grading. And then, but the current ones I'll put together into some reasonable weighted format and then share it with you so that you will know. And if you have questions, you can ask me. But you don't need to worry about all that over the break. You can come back and worry about it next week. So that's where we are regarding the grading. Yes?
I started with the LD assignment and there are a few issues that I'm facing presently.
Yeah.
So I emailed...
the issue is that who is in Maui. My students tend to be, happy kids. So one guy was married, in the middle of the semester. The other guy is now in Maui, Hawaii. So, the transmission of emails is very slow. I'm assuming you sent a mail to Yuheng.
Yeah, today morning I sent.
Yeah, and he's not going to get back to it until he comes back, which is probably on Thursday.
Yeah, he said that he can meet me next.
That's fine. Obviously, I haven't even got into LDA, so clearly, I'm not going to make the project with you before I even start talking about LDA. So you can assume that what did I say was that next Wednesday. That's obviously not true anymore. Okay, that's for sure, right? You can almost see that I would only get to LDA next Monday. So it would at least be the week after. So and it'll be fine. Okay, I think I basically wound up spending more time going back over the base network background because I think not enough people have it, and so you may as well just be on the same page. But yeah, as I said, Liu Heng will be back in town sometime in the middle of this week. And then, other questions? Yes?
Any idea what the average for the test was?
I sent the average.
Oh, okay.
I sent an email. I believe 30 something was the average and 13 is the standard deviation. Yeah, it's a high variance. Normally, any exam I seem to give, even when I think it's easy, seems to have high variance. So I don't know. So that's the variance. Yeah, I did send a mail with, in fact, the distribution and everything. Okay, so any other questions? Okay. Anyway, this is my usual Thanksgiving introduction slide, and I especially thought it was appropriate because we're doing statistics. And it is indeed the case that if you can actually, if you don't need a real picture with pink or whatever. I mean, I say pink because I don't know how many of you have seen Schindler's List. Oh my God. Okay. So there's a scene in Schindler's List where essentially people, we all feel for very specific examples we see, and then there's this beautiful scene in Schindler's List where, not beautiful actually, heart-rending scene, but all these people are being thrown out of Poland, and it's so hard, to concentrate on the tragedy of so many people. So Steven Spielberg, it's a black and white movie, and he just colors this little girl in pink, so that you can focus on that. Okay. That's I think I see Oscar Wilde basically saying that we don't need to do this if people knew how to handle statistics. Because statistics are telling you what's happening. It's just that people want specific examples. Okay, but anyway, that's a different story. And then for those of you who are not from United States, I feel compelled to tell you the story of Thanksgiving. It always was Indians giving free food to the locals. And it continues. Okay. Okay. So we are going to continue to talk about the Bayes network learning. And today's class we would basically complete that background discussion and hopefully start talking about topic models. And then starting Monday, the reading that you have done on the LDA paper would come in handy because that's what we'll be discussing. Okay. Okay. So last class we were talking about the steps in basically doing learning when given full topology and also complete examples, and we pointed out, we noticed that in that particular case, for Bayes networks with basically tabular representations of conditional probability tables, tabular representations of CPTs, it turns out that all those parameters can be learned simply as ratios of counts, because essentially when you are maximizing the likelihood becomes maximum exactly where, at the point where, essentially you get those counts, the number of, so in fact we looked at this, for example, so to get P j given A, which would be required here, right, the j given A probability would be required right here. And you can get that by, if you have a whole bunch of complete examples, you count the data items where alarm is true, and then put that in the denominator, and the data items where j and a are true, and put that in the numerator. That's it, and that you will get basically the parameter that you are supposed to have here. Once you get the parameters for all the CPTs, then you now have a Bayes network model, and then you can use it. You can forget about the examples, you can use it to predict. And of course, as new examples come in, you can update these parameters. That's a whole different point. I mean, as more and more training examples come in, you can improve your model. Okay, so that's where we were, and the steps of maximum likelihood based learning essentially involves writing down an expression for the likelihood of the data as a function of parameters. That's what we did, for example, here. Okay, we wrote an expression for the likelihood of the data given the hypothesis. Okay, and then maximizing it. And normally, instead of maximizing this directly, we maximize the log likelihood, because typically, since most of these likelihoods will be products, and so if you take logs, then it becomes sums, and then it will be very easy to basically differentiate it and find the critical points. This is useful to know since we are so much stuck with logs. In fact, it becomes interesting that when we get to expectation maximization, you will kind of again see that while logs are well behaved with respect to products, they're not well behaved with respect to
maximization.
Sums.
Yeah.
Okay, so that's why if the log of q is log of p plus log of q, but log of p plus q
Is log of E.
it's just log of p plus q. Okay, so that becomes an issue. You will see in a minute. You will see when we get to EM. In fact, as I also mentioned last class, once you get this likelihood expression, and when you try to maximize it, when you try to find the critical point where it becomes maximum, in this case, this was the best possible scenario. You almost will never see this good a scenario. Here actually the partial derivatives are all essentially in terms of a single parameter. Each partial derivative defines one single parameter in terms of itself. Okay, and so you don't have simultaneous equations, you have independent equations. And furthermore, all the partial derivatives are linear, which means you have linear independent equations, and that's as good as it gets in life. Okay, now basically you can get all sorts of other things, like for example, you can actually have nonlinear equations, and when you are having nonlinear equations, then you will wind up having to do function maximization. Function maximization, essentially, we talked about this again last class. I don't know where we are. I think we go forward. Okay, so function maximization would be finding the zero of the differential. And finding the zero of the differential can be done using essentially Newton-Raphson kind of a method. So it's not, you won't directly know the answer. You essentially have to get to the answer by gradient descent methods. Okay, now this also is considered okay if, in fact, the original function, the likelihood function that you have, has a single maximum. Okay, that means then the differential will only become zero at one point, whether it's, and so finding that 1, 0 would be easy. The bad scenario would be if the likelihood function you have has multiple maximums. And there is one of them is global, and there are many other local maximums. There, then what happens from your calculus, you know that essentially just because gradient becomes 0 and second order derivative gives you the right sign, it still doesn't mean that it is a maximum. It only means it's a local maximum. And you have to find all the maximums and find the maximum of those maximum to find the global maximum. Okay, and in particular, if you're doing gradient descent, you can get stuck at local maximums. Okay, that's a problem, and you can't help it. Okay, those are all the things that people will wind up having to do when they are essentially following these simple rules. That is, for an arbitrary hypothesis, in terms of, let's say, in our case, in terms of Bayes networks, you write down the log likelihood, you write down the likelihood, you take the log likelihood, and then find the place where the derivatives become 0, and then that would be the maximum. And if you can also prove to yourself that the log likelihood you have on your hand is unimodal, that means it has only single maximum, then the only maximum, the only 0 you found also must be the global maximum. If not, you have to actually do usual restart kind of a thing. We have to look for multiple maximums and see whichever is the best one. Okay, all of these can complicate issues. The nice thing is, for the large class of Bayes networks with complete data and conditional probability tables, where basically the conditional distributions are given as tables, all of them are important. If you have all those cases, all those conditions satisfied, then learning is almost an anticlimax. Because just basically count the number of examples, which have the property divided by count the number of examples, which have the other one. That's it. Okay. But that's just the tip of the iceberg. And we'll see today itself, actually, that it becomes more interesting as we move to EM. Okay? All of this, by the way, is for maximal likelihood. Okay? And remember, we got into ML by starting with Bayes learning. And by the end of today's class, I'll go back to Bayes learning. Okay, almost much of what we are doing here is, this is how most people do learning over graphical models. And this is actually how, this is the best, so if you know the frequentist statistics, if you know any classical statistics before you came to this class, then they correspond to maximum likelihood, maximizing the likelihood, so the ML method. Okay, and I mentioned this whole thing about how Bayes learning doesn't even have any notion of maximization, it's just inference. And we'll go back to it by the end of today's class, because LDA is just Bayes learning. Okay, so that's where we are. Okay, any further questions before I go forward? So, then basically, if I know the topology, and if I know the data, and the data is complete, then it looks like it's easy scenario. Okay, I did say that it can be a little hard if, for example, if even if you have, so there are multiple conditions: complete, known topology, complete data, tabular CPTs. Okay, all three are important. When all of them are, that's what we saw the Pearl-based network was. It had all these properties. And when all those three are there, it's very easy. Okay, and I already mentioned that if you don't have tabular CPTs, you can have parameterized CPTs. Parameterized conditional distributions. Examples can be noisy R, Boson, if it is discrete, or Gaussian, conditional Gaussian, if it is continuous. Okay, in all those cases, you will still set up the likelihood, and the likelihood equations will no longer be, the partial derivatives will no longer be linear, but you will still be able to solve them. In the sense, if you can't directly solve them, you will basically use the gradient descent methods. Okay. For Gaussian, actually, the textbook gives a worked out example when the CPT is a conditional Gaussian, and it's kind of cute to see that for a Gaussian distribution to maximum likelihood becomes maximum exactly when the counts, exactly what you would have done, where you would have taken the counts. Okay, so again, what you do without knowing the reason is actually being rationalized from a theoretical perspective. That's what we do. Okay, so if any of these, and I already saw, if any of these is violated, then the happy results won't hold. And we already talked about this being violated. Now the next question is, what about complete data and known topology? And those are actually bigger violations. Okay, so now let's start with the known topology. And in fact, both of them can be violated one at a time, or they can all be violated at the same time. In which case, that would be the hardest learning scenario for us. Okay, so let's assume, for example, let's look at unknown topology, but complete data. What does that mean? That means you know all the names of all the nodes in the Bayes network. You just do not know the network structure. Do you see what I'm saying? So it's complete data still, but the network structure is not known. So imagine that you have imagine you have the burglary, earthquake, alarm, John calls, Mary calls scenario. This is the network that we've been looking at before. But how did you know this is the correct network? I just gave it to you saying this is the network you're going to learn parameters from. If I only gave you the data, then any arbitrary directed acyclic graph on these 5 nodes is a hypothesis. Okay, in particular, here is one more. And normally we give this as the worst case scenario because this actually is also useful to see that this network requires 32 different probabilities, 31 different probabilities, because it's a complete acyclic graph. Okay, and so 31 is the 31 is basically what you would have needed if you didn't have any structure at all. Because if you have 5 variables, 2 power 5 is the number of joint probability entries you will need. You see what I'm saying? Okay. So this could have been the network, this could have been the network, and you need to figure out what is the network. And if you believe this is the network, then you need to learn 32 parameters. If you believe this is the network, you need to learn 1, 2, and 4, 6, and then 6 plus 4, 10 parameters. You see what I'm saying? The same data, but based on what you think is the network, you have to learn more versus less parameters. Okay, and so how do I figure out which is the right one? The basic idea, there are 2 ideas. One idea is to realize that whenever I put something in a network form, I am essentially stating some conditional independence assertions. Okay, if I have this network, what I mean by this is, if this is my network, then John calls must be independent of Mary calls given alarm. If this is the network, then Mary calls must be independent of burglary as well as earthquake given alarm. Because that's what comes out of the network structure, right? So if given your data, you can assess whether these conditional independences hold. Do you understand what I'm saying? Now, of course, normally to check whether a conditional independence holds, you need basically asymptotic analysis. You need large number of examples, infinite number of examples, and then check whether P A given B is the same as P A. Just because it's true in your small sample doesn't mean it is true in the large sample. Just because it's not true in your small sample doesn't mean it won't be true in the large sample. Okay, so when we're trying to assess independences based on just a little bit of training samples, then that is actually a heavy-duty statistical inference, checking whether or not, in fact, the independence that you found is actually significant, whether or not the dependence that you found is significant. And for that, again, even though I didn't talk about it here, you may have read during some time in your life the chi-square significance test. Okay, so you can use chi-square significance test to check whether or not certain independences actually are independences in the data. And if they are, then you will say, okay, I'll take that. So in particular, if I am looking between, if I'm trying to decide between 2 different hypotheses, at least I will pick the hypothesis that seems to be, whose independencies seem to be more supported by the data. Okay, that's one idea. Okay, now there's not getting away from the fact that the moment I said topology is not known, I made the problem much harder. So don't expect miracles, because I was essentially talking about double exponential number of acyclic graphs. Okay, different acyclic graphs, and you have to pick which is the right one. Okay, so here I'm just saying, at least if you think, here are the 2 possibilities. If your friend says, I think it's either this or this, would you know which one to pick? That's what I'm telling. Okay, so the idea is kind of doing the independence analysis. The other idea is to see, basically learn with respect to both networks. So if I tell you that this is a network or this is a network, then act as if this is a network, learn the parameters. Act as if this is a network, learn the parameters. Okay, now when you learn the parameters, remember, you learn the parameters such that the likelihood is maximum. Right, that's what we did, basically, when the parameters correspond to the point where the likelihood function becomes the maximum. Except the likelihood function is different here and different here. This is L1, this is L2. Now, what is interesting is both L1 and L2 are in terms of, they can be plotted on the same axis. So if the L1's maximum is better than L2's maximum, then I'll pick the network one. If L2's maximum is better than L1's maximum, then I pick network 2. Does that make sense? Okay, so I would run basically the same algorithm. I mean, I'm basically learn the parameters for this network as well as this network, compute the maximum likelihood, not only just pick the parameters, but if you go back and throw those parameters that you learned into this expression, you will get the log likelihood at that point. Right? Okay? And then compare the two log likelihoods, one corresponding to one network, another corresponding to another network. Okay, they are different expressions, but they're all ultimately in the same units, likelihood units. Whichever gives higher likelihood to the data is the one I'm going to pick. Sounds like a very reasonable thing to do. Okay, because after all, maximum likelihood is whose maximum likelihood? Making the data more likely. You're picking the parameters such that with those parameters, the data you saw is most likely to be produced. That's exactly what you do. So after two possible alternatives, you pick the alternative that will give the higher likelihood. Okay? What is interesting is, unfortunately for us, what is interesting is that if you do that, you'll always say this guy wins. That's a problem. It turns out that this guy's maximum likelihood will always be higher than this guy's maximum likelihood. What that means is if you just blindly try to pick the network which will give highest likelihood for the data, you'll always keep putting more and more links until the network becomes complete. And in doing so, what you did is you overfit your hypothesis to the data. It just exactly predicts the training data, and it's going to be useless on the test data afterwards. Okay, so basically maximum likelihood has gotten up to here, but then it just fails here because essentially the network, the more connections a network has, it will always have higher likelihood. So if you just go with ML, you will always prefer complex models over simpler models. But there is no real reason that the world is more complex than it is simple. In fact, it's the opposite. We believe that the simplest explanations are the ones that should win the day. Occam's razor says so, for example. To get that to happen, you not only must consider the maximum from this family, maximum likelihood for this family, and you got a maximum likelihood for that family, but you then for the maximum likelihood for this family plus a penalty term which is proportional to the complexity of the network. So if you reach your maximum by being a highly complete network, then you will be penalized. So if you reach, let's say, just talking in arbitrary terms, if you reach 5 units of likelihood, okay, but you have 15 links in the network, the other alternative reached 4.3 units of likelihood. So in some sense, it's actually lower likelihood, but it only has 2 links in the network. So for a significantly simpler hypothesis, you're almost reaching the same level of likelihood. I want to pick that. Do you see what I'm saying? Now, when I did this, I understand this is Thanksgiving, Wednesday before Thanksgiving, and all of us you are already sleepy, but what did we just do when we added to MLE another component? For the maximum likelihood estimate, we added another component called the penalty component.
We are trying to find a trade-off between...
I know, but have we looked at this idea before? I mean, I'll again ask today in some other case also, have you looked at this idea before? But how did we go from base learning to ML? What's the missing middle piece? What? mapped. Remember maximum posteriori, which took log likelihood of the data plus log of the prior. You see what I'm saying? Essentially, that's what we're doing here. We're saying if in fact prior over the networks is such that complex networks have less prior likelihood than simple networks, which is what I believe Occam was saying when he said, go for the simplest hypothesis. One way of viewing that is he's saying of all the hypotheses, the simpler ones have higher probability, prior probability than the more complex ones. If that is the case, then log of the complex one would be a smaller number or a smaller number than a log of the simpler one. That's how you penalize. So in essence, we already started slippery slope. We went away from base learning and huffing and puffing and went through map and said that's still hard and went to MLE. And lots of people, if you take a general machine learning course, you will spend all your time in just MLE methods. And then you will throw in something called regularization term. What's regularization? From a statistical perspective, regularization is taking the prior of the hypothesis into account. Okay, and the priors you assume are set up in such a way that the more complex hypothesis will have lower prior probability than the more simple hypothesis. That's our expectation about how the world works. But in general, essentially, as long as you have a prior, that's the way you can combine likelihood with a penalty factor. Okay? So by the time you come to topology learning, normally all the topology learning network methods have to not just do maximum likelihood estimation, but they also have to take into account some component which is best viewed really as a penalty based on the prior of the hypothesis. You see what I'm saying? Okay? So that's the point that you want to understand about topology learning. Now, of course, one way, here I said I'm giving you two different possibilities, two possible networks, and you have to pick one. But normally there may be nobody to give you any network. So what do? All the topology learning algorithms start with a random topology and he'll climb their way. Start with a random topology. Okay? And then consider either removing or adding edges. When you add the edge, you increase the penalty factor, but you also know that you are increasing the likelihood. But I am willing to add one edge if it makes a huge jump in the likelihood. That would be a good hill climbing step. And I do this until I spend some time, and then I take whatever is the current topology, the best topology I have on hand, and I just give it to you. That's how topologies are learned. You see what I'm saying? Yes, sir.
Do the topologies they start off with, are they usually sparse?
It's a good question. I think, there isn't any, different algorithms do different things. The main decisions that algorithms do is what is the penalty factor they give to the network. Initial conditions, I don't think they make a big point about it.
Well, it seems like if it was a dense topology, then that already assumes some kind of ordering upon the nodes, which could be difficult to overcome and help on the algorithm.
Ordering about the, no, actually, in fact, if you start with a dense topology, then all you're going to do is consider removing edges. And every time you remove an edge, the likelihood goes down, penalty reduces too. Okay, and that still can be a reasonable way to go. I'm not quite sure why you would think hill climbing won't work. There could be local minimas in this space. That is for sure.
Well, what I was referring to is like if we take the dense topology that's shown on the slide, it assumes that Mary Calls is actually the parent of John Calls, earthquake, burglary, and ultimately everything else, which in the actual network isn't the case. In fact, Mary Calls is a leaf node. So it seems like that would be harder to overcome.
So again, so your point is based on where the actual peak is. Okay, the place where you are starting from might make it very hard for you to reach the peak. My example for hill climbing, I don't know, I'm not at all a mountain climber. I can barely climb steps, but I understand that Mount Whitney is the tallest peak in continental United States, right? Any of you into mountain? So we are all basically not outdoorsy types, I guess. We just eat and listen. But so anyway, so I am the expert here. So Mount Whitney, I give you as having told you already the history of Thanksgiving. I can now tell you geography of the United States. Mount Whitney is the tallest peak in the continental United States. The problem is it barely rises around, over the other nearby peaks. So it's extremely easy depending on where you start from. And if you just do hill climbing, normally hill climbing, what does it do? It says where I am, any step I do, I seem to be losing height. So I must be at the top of, where I wanted to get. In fact, coming to talk about it, that's how hill climbing is done. Columbus decided that I will reach some place, and then when I find landmass, I'll call it India. And then I'll find the people, and they will be teaching computer science, I'll call them Indians. Right? and that was his hill climbing algorithm. Right? So basically, in Whitney's case, depending on the initial state you start from, hill climbing might basically have much higher probability of leaving you in one of the minor peaks than the real peak. Whereas if you are on the other hand trying to get on top of Zermatt, which is a very beautiful, that's the Matterhorn, in Disney World, that you may have seen at least. That thing is a real nice peak which stands out from the surroundings. Any arbitrary hill climbing algorithm will work there. Okay. My point is that hill climbing in general has this problem. I can't help it. So if you happen to know something about where the real solution is, then you can use it. But then if you happen to know so much, then you'll probably have a GPS. And then we'll just helicopter down onto Mount Whitney. That's the civilized way of climbing mountains. But anyway, but that's the point. So we are doing hill climbing over topologies. Okay, and that you can get stuck. There are no guarantees. Okay, it's not at all guaranteed that this is a unimodal. First of all, it's a discrete space over topologies, and it's not guaranteed that there is only one local maximum. There can be multiple local maximums, and you'll get stuck in one. And you will probably find, you're right, that if you start with this, maybe you'll never get here. Them is the brakes for starting with hill climbing. How did you know this is the right thing? The point about this is, first of all, you have to realize that learning topology is learning deep knowledge about how world operates. Okay? And we have, as a civilization, been extremely bad at doing it. Okay, I've been to this museum in Madrid where they had this list of planetary models where they have decided for whatever reason that let's start with a model with Earth in the middle. Okay, so they start with a bad initial seed. Okay, and then try to keep making it, changing it such that more and more of the experimental errors that we are finding can somehow be sponged. So by the time they get rid of like 90% of the experimental errors, the planetary model with Earth in the middle looks humongously complex. Hugely complex. And I'll send you a picture once I'm done with this when I go home. And you will say, my God, the solar model is staring at you. Well, it's staring at you now. You weren't around then. And and if you even said something like, let me put sun in the middle, Pope would kill you. Okay? And so either you did not have the creativity to think about it, or you were not allowed to. And so you kept making this bad hypothesis more and more complicated until it fits the data, overfits the data. And of course, it has zero predictive power. Because you could see by looking at this that there's no way it's going to ever guess anything like when is the next solar eclipse. But that's not what they were trying to do. They were trying to avoid getting to jail because Pope gets mad at them. Okay? But the point is, you start from, scientific hypothesis formations is a hill climbing search. All our real life search is a hill climbing search. We don't do systematic search at all. And our starting point affects where we get to. And that's the way it is. Can't help it. Okay, that's about topology. That's the easier part of today's lecture. Okay. The second one is, okay, so if you have known topology, if you have unknown topology, what you have to do, you have to go from ML to map. That's the summary. You have to go from ML to map. Okay. Now, if you have the other thing, so we took care of this, we took care of this, as to what happens when that assumption is violated. The last thing we want to take off currently is what if the data is not complete? And for this, just to make my life simple, I will assume that the data is not complete, but the topology is known. Okay, so it's like one at a time. I'm changing. Okay, and then of course in the end you have to consider unknown topology, incomplete data, non-tabular CPDs, and then you'll have a much more interesting problem. Okay, so suppose I want to give you the topology, but the data is incomplete, then what do I do? Okay, so here is a very simple Bayes network, A, B, C, and then here is my examples. Here are my examples. I'll start with a simple case where each of my examples, this example is complete, this is complete, this is complete, this is not complete. Okay, so some examples are not complete, some are complete. Let's start with that first. Then what do? Let's just think in terms of what would you have done from an intuitive perspective. Okay, so suppose I have like 10,000 of these examples and like 5% of them are incomplete. Big deal. I'll throw away the incomplete ones. I'll live with just the 95% of the data. That's what we do. We say data cleaning. Throw away all the guys which are incomplete, and then just do your hypothesis formation on the complete data. That's fine. Okay. So what I could do is, the idea is just consider the complete data as the training data. Simple idea. But then having done that, don't you feel the least bit curious as to now using these three, I figured out what the parameters are for this network. Right? I have now a toy which predicts. So it can predict the training data itself. Why wait for the test? Do you understand what I'm saying? So suppose I gave you 15 examples to practice on for the midterm. 14 of them have all the details worked out. 15th one is partially empty. Okay, so if you read the 14 ones and figured out the theory behind these examples, instead of just throwing away 15th one and going to the exam, you could also try to see, can I complete 15th one? Because if I can't complete 15th one, tomorrow there's going to be a completely empty example. And I'm definitely not going to be able to complete that if I can't even complete this. Right? And if I had any sense of what's going on in this course, I should be able to complete this partial example. The same thing for the Bayes network. So if it actually learned something based on this data, then it should be able to predict this. Right? Okay, so you should, and you may as well do that. So go ahead and learn the parameters, and then, but now that you have the parameters, we can infer the missing value. Right? If I give you the parameters prior for A and B given A and BC given B, then I were to tell you that A is observed to be true, C is observed to be false, you can compute the posterior on B. That's just a Bayes network inference. Right? And now you know the distribution over B. And if you want to, and in fact, from a statistical perspective, all you need to know is the distribution over a quantity. If that distribution is peaked, that means all its probability mass is at one value, then that is the value. If not, it keeps all the nuances perfectly preserved. Do you see what I'm saying? Okay, so suppose in this particular case, these are Boolean examples, right? Suppose this is Boolean variable. Suppose I computed the distribution for B. How will the distribution look? It will say B is true, this probability. B is false, this probability. Yes? Okay, so I would say the following thing, that just now you did. So you had an incomplete example, 1, 0, 1, right? And then you used the learned Bayes network to realize, let's say, that with 0.7 probability, this is, 1, I don't know, not 0. 1, I don't know, and 0. See, this is my incomplete example. I couldn't use it at all before. But using my inference, I realized that, well, this is 0.7 likely to be true. And so, of course, 0.3 likely to be false. I would then say that I actually have two complete examples. Two complete examples. One example is 1, 1, 0, but it's not a full example. It's a fractional example with weight 0.7. And I have another complete example, 1, 0, 0. And it too is a fractional example with weight 0.3. You see what I'm saying? So I have fractional examples now. And I can handle, just as in likelihood weighting, we could have fractional examples. Now we have fractional examples. The training data now has the fractional weights. Right? So I have done this. That's the maximum you would have expected me to do. I just predicted B. Now I would say, hey, now that I just predicted. So for example, going back to my example about 15th problem is still not completely done. First 14 were done. You read 14 and you thought you understood. So you have a hypothesis about what I'm trying to teach you. And you tried to complete 15th one. And you came up with 2 alternate completions for the 15th one. Clearly, if everything is concentrated in one place, then you know that you understood. If you came up with alternate ways of completing 15th, that means you didn't quite understand the first 14. So now you want to go back and look at all the examples, including this one, and see if you can learn better. Okay? That's what basically you would like to do. Now that we have inferred missing value, we can re-estimate the parameters. And now that you re-estimated the parameters, you can re-infer this value. Now that you re-infer this value, you can re-estimate the parameters until you get sick and tired of this. And say, I'm done. These are the parameters I'm going to stick with. Now, well, how do you stop? How do you stop basically comes back to what do you think is happening from one iteration to another iteration. You're talking about the log likelihood for the data. Okay? And as you keep going through these iterations, the log likelihood you have for the data keeps increasing. When it doesn't increase between 2 iterations, then you stop. So I'm still doing MLE, I'm still doing log likelihood. Okay? This idea is called expectation maximization algorithm. And it's been, it's written by these 2 guys, Dempster and Schaefer, and it's one of the most highly cited papers in all of science. Okay? And, of course, understanding the idea is one thing, and of course, what's important is to understand why does it work? What is the theory behind what's happening here? I'll give you some inkling of it today, but not the full theory. Okay, so that's basically what I wrote here, the fractional examples. Once I have the fractional examples, when I take the counts, I take the counts in terms of the fractional examples. You see what I'm saying? So now, for example, now suppose I have these 3 and these 2 fractional examples. Suppose I'm trying to compute what is the probability that B is true given A is true, which is one of the numbers I need, right? B given A. How do I get that? According to my log likelihood, according to all I know, B given A is the number of examples where A is true and the number of examples where A and B are true. In my examples, A is true here, here, and here. But this is not a full example. This is a 0.7 example. So A is true in 2.7 examples. Okay? And of those 2.7 examples, B is true in 1 and here. 1.7 examples, B is true. Okay? That's my new estimate for PB given A. I can do the same thing for every other number you have there. Do you see what I'm saying? Okay? And what would be interesting is actually for you to compute the log likelihood and see that after you recomputed the parameters, log likelihood would have increased. In fact, you can show it. I mean, this is just, you can just throw it into your little calculator or a computer program, and it will show that log likelihood keeps increasing as you make these steps. And then it plateaus out. And when it stops increasing, that means you have reached a local maximum. Notice I said local maximum. I didn't say maximum. I said local maximum. That's the best you can do. Yes, sir.
Yeah, why that is 2.7
What?
Like,
This example is a fractional example. That's the point.
there's another one, like fractional is 2.7.
Oh, yeah, you're right. I'm sorry. Yeah, in this particular case, you're right. Yeah, that's true. This point is well taken because the number of examples when A is true is 1, 2, 3, 4. But they're not 4 examples. They're really 3 examples. Right? So denominator is 3 and numerator is 1.7. Right? Because this is, so imagine each example has a weight, and this is the weight that you care about. It's almost very similar to the likelihood weighting that we talked about. And you are essentially keeping the, the posterior and decomputing the posterior. Beautiful idea. Okay? So that's what you'll wind up doing if you have this. And basically, this is the EM algorithm. The E step, you compute the expected values of the unobserved variables. Okay, now here's one last thing. This idea, I made it sound as if there are 10,000 examples of which, 9,000 are complete and 1,000 are incomplete. But in fact, suppose B is a hidden variable. I just made it out of nowhere. Then I will never know what B's value is. So in fact, all the examples would be incomplete. The beauty of this idea is that you can just randomly put values for B in the beginning. Randomly initiate values for B in the beginning and let EM go through its iterations. That's the beauty. Do you see what I'm saying? Okay? And that's actually the reason why it's that famous. It's not just partially incomplete data. Even if it's fully incomplete, even if you have a large number of hidden nodes, which means their values will never be known for any of the observed examples, you are completing the examples as part of learning. So in my previous 15 worked out examples, in fact, all of them have some pieces missing. In fact, all of them have the exact same piece missing. And you have to figure out what was I meaning there. And you will slowly figure it out, as sort of while you go back and forth over learning and maximization, learning and inference. Okay, so in the expectation maximization, so that's why the EM algorithm is written completely in terms of just unobserved variables. Some variables can be completely unobserved. That's fine with us. Okay, so assume that the unobserved variables in the beginning compute the expected values of the, so start with some arbitrary parameters for the network. Start with some arbitrary parameters for the network. That's the initialization step. Just arbitrary CPT values. Given the CPT values, I can then compute the posterior, with respect to the current CPT values, I can compute the posterior distribution for the unobserved nodes. Given that posterior distribution, now the examples become fractional examples. I can retrain, that means I can learn the parameters again and do this back and forth. So once I initialize, then every time else, learning will reset the parameters. Okay? To give you, okay, so let me just, before going up there, okay, so in the E step, I'll come back to this green stuff in a minute, okay? And especially those arrows. Just remind me if I don't come back. But this is an example that's fully worked out in the textbook, and I'm going to just get you enough handles on it so that you can follow it yourself. Okay? Basically, instead of the ABC network, now I have a 4-node network. Again, back to our candies. And this time, I'm only observing the flavor of the candy, the wrapper of the candy, and whether or not the candy has a hole in the middle. That's all I'm observing. I have this sinking suspicion that these candies are coming from different bags. And if I can figure out which bag they are coming from, I'll have a better chance of figuring out whether they will have holes or whether they'll be cherries or they'll be limes. I just made this up, and this is my just sinking suspicion. I have a paranoid theory that there are, even if you can't see it, there are bags. Okay? So I put my paranoia into action by putting a bag variable there. And I believe that bag is sort of influencing everybody. That's how true paranoids think. So bag is influencing flavor, it's influencing wrapper, it's influencing hole. So this is my theory of how candy world works. Okay? Now, if it's my theory, then I should be able to figure out what's my best shot for this theory. What's the best set of parameters for bag, flavor, wrapper, hole, CPTs, for all of them. Given I have this data. I have apparently 1,000 samples. Now notice that my 1,000 samples are nicely classified into this little table here, and they will only be classified in terms of flavor, wrapper, and hole, because nobody ever saw the bag. The bag exists, but nobody has seen it. Okay, right? And so you not only are paranoid, you are actually going to figure out what are the conditions under which your paranoia will be justified. Especially you're computing the parameters. That's exactly what happens when you introduce hidden variables into the network. They're hidden because no example ever sees it. And we went through this whole discussion as to why that's a good thing to do. And in fact, why some causes may never actually be seen in the observed world. And you still cannot just assume the cause doesn't exist. Okay, fine. So I start with this, and so now what do? I initialize. Now, obviously, every example is incomplete because it has no value for bag. It turns out bag is of, I guess, I don't know which ones. My bags are how many types? I think bags are just like the 5 types bags that we mentioned in the beginning, for example. Okay? And no, I think it's actually only 2 types of bags that are considered. So bag is like bag of type 1 and bag of type 2. And if you just have the probability that the bag is of type 1, then you know the probability that the bag is of type 2. That's the simpler example. Okay, so what do we do in this case? We start with the initialized parameters. You just arbitrarily, out of thin air, pick parameters and throw into them. This is where you should be happy, that any arbitrary numbers that you can put into these tables, the world won't come to an end. Remember I mentioned that the way you are asked for numbers, you will never be asked what is P of A, what is P of B, what is P A or B, and what is P A and B. Because if I do that, then you can give me 4 numbers that violate the law of probabilities. I'll never ask you those kinds of questions. I'll only ask you enough questions such that there'll always be a consistent distribution. So putting any arbitrary numbers into these tables, you have a consistent distribution. As long as the numbers are not negative and they're between 0 and 1. That's it. That's the only thing that you need to do. Okay, having done that, that's what I did here. Then I can compute. Now I have a network. Even if it's a made-up network, I have a network. So I can ask, given the examples I have seen, what is the posterior on the back? Okay, I will compute that posterior, and having computed that posterior, I will then convert the examples into the fractional examples, and then I will now recompute the parameters. The first step was inference, the second step is learning. Do this again and again. Okay? The last step, I mean, of course, I'm not going through these steps, you want to look at it yourself, but essentially it's just, simple Bayes network with posterior distribution computation. And in particular, even if you don't quite know how to do inference on the networks, if you have a tool that does inference on the network, you can just call that tool. And then you have this count taking. Your only contribution is taking ratios of counts. And you feel good because you count, you added something, right? Except next thing in a minute we'll be talking about base learning, where even that is not needed. If you know how to do inference, you're done. Anyway, so this is what I was saying. If you were to keep track of the log likelihood as you are iterating, first iteration, second iteration, third iteration, this is how that graph looks for this example. You notice that the log likelihood goes from minus 2025 all the way to a highly impressive minus 1980. You see what I'm saying? Okay, and notice that once you reach this, it's not changing that much. So it reached a sort of a plateau. So you stick with those. That's it. That's EM. Okay. Now, why does EM work? That's kind of interesting. Why does EM work? I'll only give you a piece of the puzzle. This part, obviously, you need a little bit more background on function maximization. But notice that you are interested still in doing MLE, that means maximum likelihood estimation. Your maximum likelihood is basically finding the theta values such that the log of the likelihood is maximized. Previously, the log of the likelihood was over all the variables in the network. But now, there are some J, variables called J, which are hidden variables. You never see them. So actually what you are seeing are examples that are marginalized over hidden variables. This idea of marginalization essentially says if I have both variables A and B, joint distribution will give me A and B, not A and B, A and not B, not A, not B. Those values it will give. From that I can marginalize B out. Right? And then compute the P of A to be A and B plus A and not B. That's P of A. That's marginalization. Okay? So the observed examples really are, since they are not talking about the middle, the hidden variable values, in some sense they are marginalizing the hidden variables. Okay, so this log likelihood expression essentially is being summed over the hidden variables. Just as you compute P of A for a two variable case, you compute P of A as P of A and B plus P of A and not B. That sum basically suddenly sits here. Simple. Unfortunately, if you put a sum inside the log, then you cannot be assured of simple partial derivatives having, independent, unentangled parameters with linear equations. Okay? So in general, you basically have some nonlinear set of equations, and in particular, the objective function, the log likelihood function, might be multimodal. That means it may have more than one maximum. Okay? And normally what you need to do in that case is you just do the Newton-Raphson method. You basically do gradient descent or some variation of the gradient ascent in this case, if you are looking for maximum. Gradient ascent methods. What EM does is a particular kind of gradient ascent. Gradient ascent is a fancy name for hill climbing. What EM does is a particular kind of hill climbing where the size of the step, rather than being always constant, it's sort of dynamically decided. Okay? And the example basically, this picture sort of tries to make that clear. Basically what you do is using, some properties of distributions, including the Johnson's inequality, you will wind up figuring out that there is a lower bound to the function you are trying to maximize. And that lower bound is in the form you want. It has no summations inside. Okay, so I want to maximize this, but I don't know how to maximize this. I know how to maximize this one, which is easy to maximize, and I know that this guy is a lower bound on this. So here is a function. This is actually unimodal. and it is guaranteed to be by this particular equation, inequality is guaranteed to be a lower bound. So one way of finding out this guy's maximum is to at least find this guy's maximum. Because you know, this guy's maximum has to be bigger than this guy's maximum. Because otherwise it won't be a lower bound. So when I maximized in the maximization step, I basically went on this curve and found this value. That was easy by just counts. Then when I threw that back into the network, then I'm essentially getting to this point in the log likelihood. And I redo this. So I'll again get another different lower bound, and then find its maximum until I get a version of the lower bound whose maximum sort of coincides with the true maximum of the function. That's what EM does. And so a way of understanding EM really is that it really is a hill climbing function, except it is a fancier version of hill climbing that works well for when you're doing likelihood maximization. Likelihood is a particular type of function, and for that, Jensen's inequality can be used, and this idea works very well. So in fact, if you go into serious books, such as, in fact, the best book currently on the graphical models is an 870-page book written by Kohler and Friedman. I believe I actually had the picture of that book in the beginning of the class, saying this, we'll be looking at stuff from various books, and this is, that's one of the books. And they point out to you that in some cases, actually, EM can be dominated by simple hill climbing algorithms. EM is not somehow holy. People like it. It is easy to do. It basically makes you feel as if you are sticking in the context of inference and maximization and inference and maximization. Okay, but it's really a hill climbing algorithm. So if you have a different way of directly finding the optimum of this arbitrary log likelihood, you'll be fine. And in fact, entire continuous function optimization literature will give you different kinds of ideas for doing it, and some of those can actually sometimes work well. But EM actually works well quite a bit of the time. Okay? So that is how you handle incomplete data. Yes, sir.
So this bag example can be taken as an example where we don't have full topology and neither we have full complete data.
No. Bag example, actually it's a good question. Bag example, I am saying that I gave you the topology because I decided to hallucinate. And my paranoia says bag is there. And bag is causing everybody. I'm not considering all possible paranoias. I'm only considering my paranoia and finding the best fit parameters for that. If you want to then combine incomplete data with unknown topology, then you have to have multiple hallucinations. Really take powerful drugs. And then consider different kinds of network topologies, different kinds of hidden variables which are all talking to each other. Okay, and for each one of them you can do this. And when you do that, you will notice that once again you need to go to map rather than MLE. Because you need to consider how paranoid are you getting. Do you see what I'm saying? How many of you have seen A Beautiful Mind? Yeah, so that guy obviously was clearly, in a different world. He starts seeing things in New York Times front page talking to each other and telling each other, secret messages. So you have to say that even when I'm being paranoid, I shouldn't be too paranoid because, it's less likely that 18 different people are out to get me. And more likely that only one person is out to get me. And that's again prior on the paranoias. Do you see what I'm saying?
And if you would not have taken bag into consideration, then this data would have not given that.
So that's a very good question too. So if you only consider, so the other interesting question that he's asking is, if I only consider all possible network configuration on just these 3 observed nodes, would that have been better or